included ICML, and it's titled Goal-Oriented Case Estimation for Zero-Shot Learning. I chose this paper because it's very much applicable to the problem that we're trying to solve in the B machine project, which is that we have some of our data set that are so imbalanced, and if we decide to use them as they are in our training, it's going to severely affect the performance of the model. So as a result of that, we decided to take out those species of bumblebees that are rare and embark on learning a model on them through the zero-shot learning approach. So similar thing is employed in this place. So as you can see here, the ZSL problem aims to recognize novel classes by transferring semantic knowledge from seen classes to unseen classes. Basically, what that is saying is when we have a model that is trained on classes that are known, that are well known, and we want that model to be able to generalize to samples of classes that was not exposed to the model at the point of training. So that's what this zero-shot learning problem is all about. So now, practically it's infeasible. You cannot train a model on A and expect the model to be good at classifying B. It's just not possible. So to be able to help the model to learn B, there must be something about B during the training that the model will know about. Some implementations have gone in this direction. Some they use similarity measures, some they use dissimilarity measures to learn a model that understands the differences between things. And so that when the model now sees something during inference, then the model can say, oh, this sample, this instance that I'm seeing, it's different from the training samples that have been trained on. So it can measure like a cosine similarity or a vector space model, measure the angle of the distinction between those. So the extra information that is needed is the semantic knowledge. It's built on shared between different classes. So what that's saying that instead of just learning the model, in our own case on images, then we're going to give the model additional stuff, which is the images and semantic knowledge of the images. In this case, it's normally considered as attributes of those images. So when the model is learning both the images and the attribute jointly, so that during inference, when it is given an image, the model will be able to give the attribute of that. The attribute will be the predictions of that model. And we can then use those attributes as a judge of what the unseen classes will be. So it's built on attribute share between different classes. And so that is referred to as the visual semantic embedding. When recognizing unseen images, human will also automatically gaze at a region with certain semantic clue. The deep learning models does this implicitly, even without we telling it to learn semantic attribute. For instance, in our work on the insulator classification, what the model does is it tries to find signals distinguishing features between the different classes, which are the attribute attention that is paying into. Now, but here we are not explicitly giving those attributes out. So they introduced a novel goal-oriented gaze estimation, and they call it GEM, to improve the discriminative attribute localization based on the class level attribute for zero-shot learning. Now, the problem associated with this is, how do you actually decide the number of attributes that are needed to be able to learn classification? That's some of the challenge here. But they experimented with some benchmark data set, which others have worked on, and they discovered that their approach is better. So that's the introduction to the problem. Now, the ZSL problem can be categorized into conventional or generalized setting. As we can see my mouse cursor. In conventional zero-shot learning, the test images belong only to unseen classes. So that's the difference there. That is, the test images is not part of the training images at all. But for the more practical and challenging generalized ZSL, the test images may belong to both seen and unseen classes. So in that scenario, you could have the test messages, images belong to both the same classes that are used during training or the unseen classes. So the semantic descriptions, which are the attributes, they are shared information between seen and unseen classes, and that ensures the transferability of knowledge. Okay, so I will go now into detail of the implementation that they use. So here is the detail. Here you see this is an input image X, and you have the attribute. So a list of attribute here, like a bag of words. It is bill shaped, curved, back color, rufous, head pattern plain. So that's the GS is an end-to-end training model with two main parts. We have the gaze estimation module and a plain ZSL backbone. So here they pass the image into an encoder, which encodes and tries to compress the image into a lower level representation. And also, they also learn an encoder on the attribute using word-to-vec and multi-layer perceptron. So this goes through the attention module to be able to learn where in the image the attribute actually corresponds to. And you also have here the attention transition, and they measure the cosine similarity, like I was mentioning before, that is between the two vectors, trying to measure how similar the image is to the learned attribute representation. And you have the attribute localization, and they are optimizing the mean square error as the objective function. And you can see here you have a list of predictions of through a back propagation, because you actually back propagate this back to optimize the weight of the model. So here you have the attribute that most correspond to that particular feature, high color black. And this is used to optimize the attention span. So now they perform experiment on pre-data set, as we can see in the result. I want to go to the experiment. So they use three widely zero-shot learning benchmark, which is the CUB 200, 2011, the sun attribute and animals with attribute. And the result of their performance of their architecture is as shown here, as we can see here. So you have divided it into two, the zero-shot learning and the generalized zero-shot learning. And these are the highest that are shown in red here. So on the three data set. So they have a relatively comparable performance with existing method in this domain. Okay. Now they did some ablation study on the different component because this is a multi-component architecture. As we can see, we have here you have the gaze estimation module, which measures the cosine similarities, and you have the feature extraction, and you have the cosine similarity for classification of the input image. So these are some of the modules that make up the entire architecture. One interesting thing is that these modules are optimized simultaneously, so which makes it possible to train this from end to end without needing to break. So that's essentially what this paper is all about. Majority of the components there are standard components that we all know in deep learning, like the word encoder, the attention module, which actually pays attention to where the model is looking at the time of decision. So that's all that I have to say. Any questions?